In this last section of chapter 2, we're going to talk about another method for taking the derivative, and this is called implicit differentiation. So what we have been doing so far, even though we didn't come out and call it that, we've been doing what's called explicit differentiation. Now that is when you have an equation where y is explicitly defined as a function of x. So you can find the derivative directly. So what I mean by that, if you look at this example right here, we have y on one side and all the x's on the other. This is where y is explicitly defined as a function of x. So then when we take the derivative, we can find it directly by just taking the derivative of each term. Now, when you don't have a function that is explicitly written in terms of x, this is called implicit. So we're going to use implicit differentiation when the equation is not explicitly written as y equals and then everything else on the other side is in terms of x. So when you take the derivative of both sides, you don't have it set up so you have dy dx is equal to and then your derivative. This is when we're going to have to do a little bit of extra work to solve for the dy dx. So an example of that would be down here. So this is not explicitly defined in terms of x. We have x and y mixed together. And now that could go for any variable. When we say x and y, we intuitively think about independent and dependent variables. Just remember that could apply whether we're using p's and t's or s's and r's. Just be aware that you have to understand what is your independent and what is your dependent variable. Now, the majority of the time that we use implicit differentiation is usually because we have an equation that does not represent a function. So, for example, a circle, x squared plus y squared is equal to r squared. So, not always, but usually we use implicit differentiation when we're dealing with equations that don't represent a function. Looking at the first example here, we have an equation 3x to the fifth plus 2y to the fourth plus y is equal to 37. And the question is asking us to find y prime, meaning the derivative of y. And then we want to evaluate it at the point x equals 1, y is equal to 2. Now, because this equation is not set up, so we have y equals, then all the x's are on the other side, it's not explicitly defined in terms of x, we're going to use implicit differentiation here. So, because we have it defined here as 2y to the fourth, and we know y is equivalent to something else in terms of x, we need to use the chain rule here. So when I take the derivative of 3x to the fifth, that's this here. X is our independent variable, so I'm not concerned about using the chain rule here. X is not equivalent to some other expression. So when I take the derivative, I can just take it like we normally do, and I can bring the 5 down in front. That gives me 15 x to the fourth because I take that 5 and decrease it by 1. When I take the derivative of the second term, y is equivalent to some other expression. So when I take the derivative of this, I need to use the chain rule. So I'm going to bring the 4 down in front, that's 8. And then I decrease the 4 by 1. So that gives me y to the third. But then this y prime is here because then I have to take the derivative of y. Now, in this example, the author of the book is using prime notation. You could also put in there dy dx. You can use whatever notation you want. Just remember that this is the derivative of y. Now, when we take the derivative of the next term, that's y, I just get 1. But because we know y is equivalent to some other expression, and we have like an inner function here, I have to multiply by the derivative of y using the chain rule. So when I take the derivative of y, because y is the dependent variable here, I'm going to have 1 times the derivative of y. Then I bring down my equals, and now when I take the derivative of 37, that's just going to be equal to 0. Once I've taken the derivative implicitly, now we have to solve this for y prime. We're trying to find the derivative of y, and I've got a y prime here, and I've got a y prime here. So in order to solve for y prime, we're going to put anything that has a y prime in it on one side of the equation, and then anything that doesn't have a y prime in it on the other side of the equation. So in this case, I'm going to subtract 15x to the fourth from both sides. So now this side has all the terms with the y prime in it, and then this side has the terms without the y prime. Now the strategy behind doing that is now I can factor out the y prime and divide by what's left over. So when I factor out that y prime, what I'm left with is 8y to the third plus 1. Now I just divide both sides by the 8y to the third plus 1. And here is our derivative. So in our derivative, we see x's and y's. This isn't always the case. Sometimes you'll just get x's. So just be aware of that. But a lot of times you'll see x's and y's mixed together. Now, if we want to evaluate the derivative at the point 1, 2, that means everywhere in here, I need to put in 1 for x and 2 for y. Here's the notation we use for that. It's y prime, and then this line is a way of letting the reader know that we're going to evaluate it, and then down here tells us what we're going to use to evaluate it. So x is equal to 1, y is equal to 2. When we plug that in, we're going to get negative 3 over 13. So this is the instantaneous rate of change on this curve at the point 1, 2. Or another way you could look at it, remember, is that this is the slope of the tangent line at 1, 2 on this curve. Let's look at another example. Example 2. We have x squared y to the third minus 3x plus 4y is equal to 10. And we're going to find y prime. So I need to take the derivative of each term. And then as I do that, when I take the derivative of y, because we know y is equivalent to some other expression, because it's the dependent variable, we have to use the chain rule. So when I take the derivative of this term here, one thing that you need to recognize is for this one, you're going to have to use the product rule because I have x squared times y cubed. So when we take the derivative of this, I'm going to take the derivative of x squared times y cubed plus x squared times the derivative of y to the third. So this is using the product rule. And then, of course, we can carry down all the other notation. So we would take the derivative of 3x, the derivative of 4y, and then equals to the derivative of 10. Everything else gets dropped down. Now, when I take the derivative of x squared, x is the independent variable, so I don't need to worry about using the chain rule with this. So I have 2x times y cubed plus x squared, that's this here, times the derivative of y cubed. Because this is a derivative involving y, and we know that y is some other expression, this is where we need to use the chain rule. So when I take the derivative of y cubed, I bring the 3 down in front, decrease the exponent by 1, that's 3x squared, and then multiply by the derivative of y. So that's where this y prime comes from. So we have x squared. The derivative of this is 3y squared y prime. That's this. Now, when I look at the derivative of 3x, I have minus 3. The derivative of 4y is 4. But because we have y here, that is the dependent variable, I have to make sure that I multiply by the derivative of y. And then this 10, when I take the derivative, because it's a constant, is equal to 0. So looking at this, because we're using implicit differentiation, we're going to have to now solve for y prime to find the derivative. So anything that has a y prime in it, you want to keep on one side, and everything else that doesn't have a y prime in it goes on the other side. So we're going to add 3 to both sides and then subtract 2xy to the third from both sides. So now on the left, we have all the terms that have a y prime in it, and everything else is on the other side. So then what we can do is factor out the y prime and divide by what's left over. So here's our derivative, y prime. That's the derivative of this curve right here. Now we're going to apply implicit differentiation to a topic called related rates. Now, related rates deals with problems in real life where we have multiple variables changing with respect to time. And so these problems can seem complex at first because you've got multiple moving parts, but once you see the steps and break it down step by step, you'll be able to see the relationship between those variables and figure out how to solve for the unknown. When you're trying to solve a related rates problem, the first thing you want to do after reading the problem, of course, is identify what the variables are. You want to look to see which variables are changing with respect to time. You want to see how the variables are related to each other, and you want to look for any constants that are involved in the situation. The next step is that you want to set up an equation. Sometimes that's given to you in the problem, sometimes it's not. So if it's not given to you in the problem, then you have to analyze the situation and determine what equation would best represent the situation. Once you set up the equation, then you want to take the derivative of both sides. If you're given any known values, then you want to make sure you plug those in as well. And then once you have that all set up, you can solve for the unknown rate. The only way that you're going to get good at this is by practicing and jumping in. So let's look at this example 3. In this question, it says, suppose both y and x are differentiable functions of t, and that the relationship between x and y is expressed by the equation 4x to the third plus 3y to the fifth is equal to 960. We want to find and interpret dy dt when dx dt is equal to 4, x is equal to 6, and y is equal to 2. So in this first example here that we're using with related rates, this is a fairly straightforward one to get started off with. The equation is provided for you, so that makes it a little bit easier as well to get started. So we're going to start with this equation right here. The goal is to find and interpret dy dt. Now, when we identify what the variables are, we can see that we have x and y, and in this explanation here, it tells us that y and x are changing with respect to time, with respect to t. When you go to take the derivative of this, we're going to use implicit differentiation. So we're going to take the derivative of each term. So when I take the derivative of 4x to the third, that's going to be written like this. And I'm going to take the derivative of 3y to the fifth. That's going to be written like this. And then, of course, the derivative of 960 is 0. I want to point out that, again, these are given as functions of time. These are changing over time. X is a function of time. Because x is changing with respect to time, when I take the derivative of 4x to the third, we need to use the chain rule. So when I take the derivative of 4x to the third, I have 12x squared. Using the chain rule, I multiply it by the derivative of that inner function, a function x with respect to t. This is why when I write down the derivative, I have dx dt. When I take the derivative of 3y to the fifth, I get 15y to the fourth. I'm taking the derivative of y, but y itself is a function of t. This is why when I use the chain rule, I multiply it by dy dt. This is just a constant that's not changing, which is why we're going to find the derivative here as 0. So when I take the derivative of both sides and I take the derivative of each term separately, this is what we get here. We kind of worked it out individually up here first. So the derivative of 4x to the third is 12x squared dx dt. The derivative of 3y to the fifth is 15y to the fourth dy dt. And then that's set equal to 0 because the derivative of 960 is 0. Now the problem said to find dy dt and interpret what it means. We have to isolate the dy dt. I'm going to subtract 12x squared dx dt from both sides, and then I'm going to divide both sides by 15y squared. That will isolate our dy dt. So this tells us that the derivative of y with respect to t is negative 12x squared dx over dt, all divided by 15y to the fourth. And then, of course, we can simplify it by dividing both the top and the bottom by 3. Now, to figure out what the value of dy dt is, we're going to plug in the values that were given to us at the beginning in the question. We were told that dx dt was 4, x is 6, and y is 2. So when we plug all that in, we get that dy dt is equal to negative 7.2. So we've got two moving parts here. We've got y is changing with respect to t. We've got x is changing with respect to t. And when we isolate just the way that y is changing with respect to t, we get this negative 7.2. If t increased by 1 unit and dx dt is 4, x is equal to 6, and y is equal to 2, then the value of y is expected to change, and it has a decrease of approximately 7.2 units. So when all of these things come together, and t is increasing by 1, because remember we have this over 1, we have a decrease in y by 7.2. Now, let's look at a related rates problem that is actually in the context of some real-world problem. So we have oil is leaking in a circular shape from a tanker in such a way that the radius of the circular spill is increasing at a rate of 2 feet per hour. To manage the spill, the oil company needs to know the rate at which the area covered by the oil is increasing. Find the rate at which the area is increasing at the same time that the radius of the spill is 600 feet. So we've got an oil spill. The area of the oil spill is a circle and it's just expanding. And so we have a couple of things that are changing here with respect to time. We have the area of the circle is changing with respect to time, which also means that the radius is changing with respect to time. Now, because we're dealing with circle here and we want to see how the rate of the area is changing, we are going to use the area of a circle. So this is the case where in the problem, we're not told what equation to use. We need to think through it and set up our own equation. And we should know, because we're trying to find the change in the area, that we need to find the area of the circle. That is the equation we want to use here. So the area of a circle is A equals pi r squared, A for area. And so when I take the derivative of both sides, remember, A and the radius are both changing with respect to time. So when I take the derivative of both sides, A and R are both functions of time. So I have to use the chain rule. When I take the derivative of A, it's just 1. But because A is a function of time, we need to multiply by the derivative of the area with respect to time. So this is using the chain rule. Then pi, that can just come out front here. When I take the derivative of r squared, the 2 comes down in front, and then r is decreased by 1, and then I have to take the derivative of r with respect to time. Since the question is asking us to find how the area is increasing, what we need to find is the change in the area. That's the derivative of the area. So that's my dA dt. And this one's nicely already set up for that. Sometimes we have to solve for it, but this one is already isolated. So now we just have to figure out what the value is on the right-hand side. We want to figure out how the area is changing specifically when the radius of the spill is 600 feet. We also know that we want to find the way that the area changes with respect to time when the radius of the circular spill is increasing at a rate of 2 feet per hour. So this is our dr dt. This tells us how the radius is changing with respect to time. So that's going to go in here for the dr dt. And we would get that the area is changing with respect to time. It would be 7,536 square feet per hour. Now, if we were told how the area was changing with respect to time, and the question asked us to find how the radius is changing with respect to time, then we would have to do a little bit more work to solve for dr dt. So I would have to isolate the dr dt to get that answer. So pay attention to what the question is asking you to find so that you know what you're trying to solve for. Example 5, it says a manufacturer of a precision instrument has determined that when the price of an instrument is P in hundreds of dollars, it will sell X of those instruments each month. The demand function relating P and X is, so here's our function here. So that means we plug in the price of the instrument in here, and we would get out the number of instruments that are sold. Due to inflation and the changing labor costs, both P and X depend on time. Find the rate at which the number of instruments sold is changing with respect to time. They're asking us to find the rate in which the number of instruments sold is changing with respect to time. Since the number of instruments sold is represented by X, we want to find the derivative of X with respect to T. So we need to find dx dt. Now, they're also giving us additional information that we can use to evaluate. They're asking us to specifically find the change in the instrument sold when the price of an instrument is $400 and the price is changing at a rate of $1 per month. So we know the value of dp dt. It's the rate in which the price is changing with respect to time. So we have to take the derivative of X with respect to T, and that's what we're trying to find. So when I take the derivative of X, I get 1, but because we know that X is changing with respect to time, I have to use the chain rule. So I'm going to also take 1 and multiply it by the derivative of X with respect to T, and that's equal to 2,000 times the derivative of this expression in the denominator, which we can rewrite to make it easier as 2p squared minus 5, all raised to the negative 1/3. The negative is because this is in the denominator and we're flipping it up, and then the 1/3 is because this is the cubed root of 2p squared minus 5. So we need to take the derivative of that and then the derivative of 350. So this is going to be the only thing that's a little bit messy. I'm going to bring the negative 1/3 down in front. The inside stays the same. The negative 1/3 gets decreased by 1, so that's negative 4/3. And I have to multiply it by the derivative of this inner expression. So that gives me 4p. This negative 5 drops out. But then in addition to that, this is where it's tricky because we took the derivative of an expression with p in it, and we know p is changing with respect to time. Using the chain rule, I also have to multiply by the derivative of p with respect to t. And then, of course, the derivative of 350 is 0, and the 2000, I just bring that down. So that was the tricky part. We had to basically use the chain rule twice. Once when we took the derivative of this, and then a second time when we took the derivative of that inner function because we know p is changing with respect to time. Once we clean it up and we plug in our values, let me scroll to the next page. We know that p is going to be 4. We know that p is going to be 4. Let's back up a second. Because remember, it says p is in hundreds of dollars. So that's another little tricky thing that you have to pay attention to. Because some people might want to directly plug in 400, but p is defined in hundreds. So we only want to plug in 4 there. And also we're given that the price is changing with respect to time of $1 per month. So when we put that in terms of hundreds of dollars, the change in p with respect to t is going to be 0.01. Once we plug in those values, we're going to get approximately -13. So what that tells us is that when the price of the instrument is $400 and it's increasing at a rate of $1 per month, the company can expect to sell about 13 fewer instruments in the next month. This is per month because remember it's dx dt, so this is the change in instruments per unit of time. The unit of time that we're using in this problem is month. And so I'm going to imagine that this -13, even though it's not written there, is over 1. So it's going to be a decrease of 13 instruments per month. Now this last slide shows you how you can use GeoGebra to check your derivatives when you are finding the derivative using implicit differentiation. So we're going to do this by hand, and then this is the way you can check it on GeoGebra. So we have y to the third minus 5x squared is equal to 8. We're going to find dy dx. Y is changing with respect to x. When we take the derivative of that first term, we're going to get 3y squared dy dx because y is changing with respect to x, so we have to use the chain rule here. X is not changing here with respect to anything, so when I take the derivative of 5x squared, it's just going to be 10x. And then, of course, when I take the derivative of 8, it's just going to drop out and be 0. So this is what we have right now. And then when we solve this for dy dx, I'm going to add 10x to both sides and then divide both sides by 3y squared. So dy dx is going to be 10x over 3y squared. Now, when you use GeoGebra to check your answer, you're going to use this command here, implicit derivative, and you're going to enter what it is that you're trying to take the derivative in here. Now, notice the way that I have it set up here. When you use implicit derivative on GeoGebra, it's expecting you to put in the entire equation on one side if 0 is on the other. So you first have to set up your equation so everything is on one side and 0 on the other, and then plug that in here. So if this is the equation that we're trying to find the derivative of, we need to subtract 8 to the other side so that everything's on one side, 0 is on the other, and then put that in there. Implicit derivative is not expecting an equal sign. So if you put in the entire equation, it's going to give you an error message, which is why you need to solve it so that it's equal to 0 before you enter in your expression here. Then when you hit enter, you will get the derivative, And as you can see, although it's in a little bit of a different form, it pulled the 10 out in front, it's the same answer. So you can use GeoGebra to check your work when you're doing derivatives using implicit differentiation.